see. There's time limit on this? I'm reading, oh my goodness, a lot. Okay, so welcome back. There were some technical problems. Apparently the technical aspects were not ideal last time, so I have multiple I have 3 cameras going today. Hopefully one of them will work. And I also have, what happened, by the way, did I have glasses or what happened to my glasses? Are they? I'm going to unplug this and plug it back in so nobody trips over it. This goes with that. So there were also, I mean, I didn't have a bunch of things to fix from last class. Maybe someone was starting to catch one of them, but so let me see. The setting was we had a metric space, and we have a curve in the metric space, and so the length of the curve I define supremum over natural numbers and a supremum over partitions of the curve. And so, the first thing to notice about this definition is if you take k equals 1, then what you get is at least the distance between the endpoints. And and even if you might even modify the definition so to have if you insist the partition get finer and finer, you would still have this bigger than that by the triangle inequality. And so we usually call sigma is called minimizing geodesic. Equality holds. So in other words, if length i.e. length sigma distance between its endpoints. And the other thing to notice about this definition is that, as in Riemannian geometry, if you reparameterize the curve sigma by a non-decreasing function s, continuous, then this sum isn't going to change. At least the supremum isn't going to change. And so this is invariant under reparameterization. And so you can always, when you have one of these minimizing geodesics, you can always parameterize it by its length. So after reparameterization, by after, let's say, constant speed reparameterization. Constant reparameterization. Sigma geodesic. And then basically one of the things I showed last class was half of a lemma, the other half of which is trivial. Sigma is a geodesic if and only if the distance between sigma s and sigma t, fraction s minus t of the distance between its semicolons. And actually, you can put less than or equal to, because if you can do this for all curve S and T between 0 and 1, you find the equality will hold the truth. And so, I mean, one direction is clear. If you have a constant speed parameterized minimizing geodesic, then this holds with equality, and the converse we showed last class. And the examples, so I gave some examples last class. Well, the one example that let me modify the example slightly. So let's take omega to be, or let's take m to be an Rn, and dp to be the peak power of Euclidean distance, d between 0 and 1. And right, so I had another definition, which is sometimes called the intrinsic. But before that, let me. So it's called the intrinsic or induced distance, d tilde, between x, y, is basically the infima over all lengths, over all continuous curves with the fixed endpoints x and y. And so the remark was that the remark should have been that dp tilde, well, it can be different things. So it's t if t is 1, and m is convex. And it's probably not equal to d, but it's clearly, because of this inequality, d tilde is always bigger than d. And so it's equal to plus infinity or 0 if t is strictly less than 1 and x not equal to y. And of course, equal to 0 if x equal to y. And then there's what happens if m is non-convex. So that you'd have a picture like this. So it's still is always bigger than d. But so I guess in these cases where p is strictly between 0 and 1, this is topologizing into discrete topology. So every point is completely isolated in that. And so if you have something non-convex, you have an x like this. This is your m. You have an x and a y here, and of course the d distance is when p is 1. The d distance is the Euclidean distance, but the d tilde distance, you have to look at curves that stay inside m, and so it would be like the Euclidean length of the curve does this. So that's the other kind of example in mind. And then you can see the question of whether or not this hint is attained is, in this non-convex case, is a question about whether or not M is compact or closed. You know, if it's not closed, the hint is not going to be attained. So big, the hint is not going to be attained. This part of the segment won't be in the set. And so that's another example of what distinguishes a length space from a. So a length space was a space in which d equals d tilde. A path metric space or a geodesic space was a space in which the int is attained. And you can see examples of values that are one and not the other here. Okay, and then the other thing we did last class was we showed that the Wasserstein distance on a, and you can see why I wanted to set from this example makes clear why I wanted to set it convex again. The Wasserstein distance on a set of measures was actually a length space and a geodesic space. Questions? So, are there questions about that? And the other bit of damage I wanted to fix from last class was about the area and co-area formulas. So I stated some version of the area and co-area formulas, but the main point, so I stated trim Evans and variety. That if you have a Lipschitz map between two spaces, and then you have a measurable subset of the first space, so I said, well, the integral of the Jacobian of the map over the first space, or the subset of the first space, is an integral over the second space, and then its counting measure of A intersect pre-images of Y integrated with respect to n-dimensional measure in Y. That's the area case. And in the case where the dimensions are reversed, so you're mapping into a lower dimensional space, so I should have drawn some pictures of this, which I will do. But I didn't say much about what Jacobian was. So what's the point? The point is that when the dimensions are different, the derivative of f is a rectangular matrix. And so the best you can hope for is the rank of this matrix is either n or m, whichever is smaller. And so in order to get a Jacobian, you need to multiply this thing either by its adjoint, and then so the Jacobian of f is basically so when you multiply this by its adjoint, you get a square matrix, either m by n or n by n, depending on whether you pre-multiply or post-multiply. But you want to have non-zero determinant. And so you have to pre-multiply or post-multiply, whichever order gives you the smaller matrix. So you do one of these things if, and you do the other one depending on the dimension, how the dimensions are ordered. And I might switch them up, I don't know. But you multiply them whichever order gives you the smaller square matrix. And so that's what goes on the left side of this formula. And so Isabel asks a question, which was let me try to draw an example. So let's say if n is 1 and m is bigger than 1. So then what I'm doing is I'm mapping a curve into 2 or 3 dimensional space, or maybe even higher. And I guess that's this case here. So what this determinant is doing is it's measuring, if I take some small interval in this curve, yes, some subinterval, how much is it being stretched out when I map it over here? And so basically what this says is, so if the Jacobian is large, it means this thing's being stretched out a lot. And so the quantity on the left is going to go up. Now the quantity on the right, I'm measuring, this is length, so I'm measuring the length of the curve on the right. And what the formula is telling me is that the stretching here, the integral of the amount of stretching here coincides with the length of the curve on the right. Except in regions like this, where that part of the curve is covered twice by the image from here to here. So when I count up like this curve, I need to count this part twice when I do the integral over there. And that's why I have to do this counting the number of pre-images of y over here. So that's basically the area case, the so-called area case. Now the Choreo formula is the other direction. So the Choreo formula is like, imagine, well, we could do it. Let's take m to be 3 this time. And so n will be either 1 or 2. So you could think about, let's take n if you want, let's be simple. So I could have a curve, say the unit circle. And then I could have, let's do n equals 2 and n equals 1.
But for this example, don't we want n bigger than m? Because we did an example of n smaller than m.
Oh, yes, thank you. How's that? Thanks. So this time my map f is going to go in the up. So let's say it might take some region up here. We could even take this to be the region A, I suppose. And I could think about something, I could think about a map like radial projection. So f of xy could be xy over square root of x squared plus y squared. So what that does is it takes every point, you look on rays through the origin, that would take all these points here to this point here. And similarly, it would take all of these points over here to maybe that point there. And so what the Choreo formula says is that if I want to calculate, well, again, so what's the Jacobian saying this time? The Jacobian is telling me how much compression I get when I map from here to here. Now, it's not measuring compression in this direction, but it's measuring compression in that direction. So if I take a region over here, how much is mean width going down when I project it to there? That's what the curve is measuring. And so if I integrate that compression over this region, what the Choreo formula is telling me is that that's the same thing as integrating with respect to arc length along this segment, but then I need to integrate a factor against arc length, and the factor is basically the difference, and in this case is 1, the factor is the length of these curves. And so it says if you integrate against arc length of the segment, the length of the curve that's projecting to that segment, then what you will get is the total area of A weighted by the amount of compression that's taking place in the angular direction. So I thought I should use some examples. Great. And another form of this, another statement, an equivalent statement. So here it's like I took the test function to be to be characteristic function of A. I could also write these formulas with an arbitrary L1 test function. So the corollary. The integral of E Jacobian of F X is equal to either integral over Rm of sum of get the preimages or integral over Rm integral over preimage of Y with respect to H, let's say d of X with respect to the n minus m measure of X, and then integrate all of that with respect to the m measure of Y. So this is n, it's bigger than m, and it's less than equal to m. So I wanted to apply these guys to our geodesics in the two Wasserstein space on a convex subset within space. So what we saw was that we saw that the set of probability measures on M metrized by the two Wasserstein distance is a geodesic space. And we saw that with IS pushing forward gamma, two geodesic with gamma squared optimal. So maybe I should say and I mentioned there's a converse to this. So conversely, so what does it mean to be a D2 geodesic? It means that the D2 distance between any intermediate points here is a fraction of the D2 geodesic between the endpoints. So conversely, if let's say 1 over S, 2 of not S equals to 1 over 1 minus S, 2 of S1. So if there exist measures 0 US and U0 and U1, that fraction of the whole distance. Then I claim that then there exists some triple measure a triple probability measure such that these various projections, like I'm running out of good notation. EI comma EJ project sigma is in gamma of UI J, where I and J here belong to 0, S, and 1. And not only does it have the right marginals, but so this guy would be the optimizer between any one of these 3 pairs of measures, and sigma almost every triple X, Y, and Z echoes this relationship here. X minus Y over S is equal to Y minus Z over 1 minus S is equal to X minus Z. So on the one hand, we showed these things were reviewed essays, and what this converse is doing is it's saying that any guy that divides this thing, any sort of midpoint between these 2 guys, which divides this length in half, because that's 1/2, actually comes from some optimizers. And the proof of this converse is another application of the gluing theorem. So let gamma 0S and gamma S1 be optimizers. And then you define sigma by gluing. By disintegration of gluing. So this echoes the proof that we saw on the triangle inequality for E2. I want to disintegrate gamma 0S with respect to the middle measure mu S. And then I have some conditional probabilities, gamma 0S condition on Y, gamma and gamma S0 similarly. So again, conditioning on Y, and then define sigma by, if I have an arbitrary test function, and I want to know how to integrate against sigma, I would integrate with respect to the middle measure, and then I would integrate it with respect to the conditional first and third measures. And then you would go back to our proof of the triangle inequality for D2. Well, so this the projection of this measure sigma I just built onto the first and third variable clearly has the correct marginal. It has marginals mu naught V1. And so I can use it to estimate E2, U naught, U1. So that will always be less than the, let's say, the L2 distance between XZ, LP. And then I can use the triangle inequality, so this is less than. And the Minkowski inequality tells me that that's less than. And finally, because these guys were chosen to be D2 optimal, this last thing is exactly the D2 distance between U naught and US plus the D2 distance between US and U1. And you know what the conditions for equality are in each of these three inequalities. And when you go back and look at the conditions for equality in each of the three inequalities, come out. So, so there's somehow things I wanted to clean up from last class. So then I want to talk about other questions about that. Then I wanted to talk a little bit about geometric inequalities. And so let me tell you, maybe some of you have heard of the Minkowski inequality. By the way, there are no questions on the chat.
No, not so far. But I can ask.
Anyone familiar with the Minkowski inequality?
Yes.
And what does it say?
It says, well, a version says that the Lebesgue measure is log concave, right? With respect to the Minkowski zone.
Did you say log concave?
Yeah, but with a power, right?
So, so if you have two subsets of Euclidean space, simplest version of the Minkowski inequality tells me that if I take the nth root of the Euclidean volume, bounded below by the nth root of, so sort of a backwards triangle inequality. And you can sort of see the direction the equality has to go if you think about the case where K is like a sub. Think about the case where they're both in R2, but K is horizontal and L is vertical. So then these volumes are both going to be 0, the areas. But when you add them up, you get something like a unit square. So that's not possible. And this is kind of a this geometric inequality has an algebraic analog. And the algebraic analog says if you have a matrix which is symmetric and positive definite, or maybe two such, yeah, let's say two such matrices, I, A0, and A1. Right. Well, okay. So I could also, as Joachim said, I could also look at volume of a convex combination of K and L. And so if I applied the preceding inequality to this convex combination, I would get 1 minus SK plus volume SL. And so the volume scales like the nth power of S, but since I'm taking an n minus 1th root, an nth root rather, I can pull the S and 1 minus S through. So you can also, and this would hold for every S between 0 and 1. So I can also, so it's a kind of concavity statement for the And so the algebraic analog of this concerns n by n matrices, and it says that if I take the nth root of the determinant of a0 plus a1, again, what I get is bigger than the 1 over nth root of the determinant for sky and 1 over nth root of the determinant for phi. And this, the algebraic guy is not so hard to prove, right? The algebraic, because matrices, symmetric matrices have real eigenvalues. They're positive eigenvalues in the case, or negative in the case of non-negative definite matrices. So, so let me actually prove the algebraic analog. So let's see. So the first trick is that you can factor out the determinant of one of the two guys. Let's pretend this inequality is strict so that they're invertible. We can obtain the other case by adding a little bit to one of them and then taking a little bit that we got goes away. So as long as they're invertible, I can factor out the nth root of the determinant of a0, and I'm left with the nth root of the determinant of the identity plus something like a0 the negative square root of a0 conjugating a1. And this is again a symmetric matrix, and it's still non-negative definite. And the advantage of doing this, if I could prove it in this situation, so if that were true in this situation, if this were true in that situation, then I would get determinant of the nth root of a0 multiplying everything. Determinant of the identity matrix is 1, and then I would get the nth root of the determinant of this product. But a product, a determinant of a product is a product of determinants. So I get and then I multiply back through by this guy, and I have what I want. So the general statement follows. If I can prove it for matrices of the form identity plus b would be symmetric and positive definite. Okay, so let's do this case. So let B1 the n, let the eigenvalues. And then so what I'm trying to show is that dominates 1 plus. By the way, the advantage of this form, as opposed to the original form, is that you can simultaneously diagonalize these two matrices, whereas you can't simultaneously diagonalize a1 and b0 unless they're mute. So this guy is this is what I'm trying to show. This guy is the product of I coming from 1 to n of the i's nth root. And this guy is the product 1 plus bi, I coming from 1 to n. And so let me divide through by this side. And what I'm asking is 1 bigger than product of 1 over 1 plus bi, I times 1n, that's root, plus product of I times 1n bi over 1 plus bi. So does anyone see what to do with this? Let's see, let's do this thing slowly. So there's a natural thing to do when you see an nth root of product of n numbers.
The geometric mean?
Yeah, so you want to use the domination of the geometric by the arithmetic mean. So the arithmetic mean geometric mean inequality tells you this product is less than 1 over n, the sum of the eigenvalues. And similarly, this product is less than 1 over n, the sum of 1 over 1 plus the eigenvalues. And then you add these two things up, and the 1 plus the I here cancels the denominator, and so this is exactly equal to n over n. And you can see, I guess you can see the conditions for equality here are that in the domination of the arithmetic by the geometric mean, you want all the eigenvalues equal to each other, so you need the ratio of bi to 1 plus bi to be constant, to be independent of I, basically means that the bi's are all equal. So strict, unless b is some constant times the area of the matrix. And so what I'd like to see is that I'd like to see that this geometric analog into which the geometry of the subsets A and L of Rn have to come into play in some way is actually a reflection of this algebraic fact. So I mean, of course, it's clear that if I take P and L to be ellipses with covariance matrices given by the A0 and the A1, then this geometric fact produces this algebraic fact, but I'd like to see it for more general sense. And that's where my D2 geodesics are going to help me. I'm going to have a little digression into displacement into the subject of my PhD thesis. So what I'm interested in is convexity of various functionals along the space of D2 geodesics.
Wait,
Yep.
Intuitively, why are we going to use geodesics? I remember the proof of the Minkowski, just like you transport to the ball, and then you basically do.
Well, you're telling me the proof of the isochronometric theorem, maybe.
Maybe. Yeah. All right.
So I did a little digression. So in fact, your
Yeah.
digression is right in the sense that the Minkowski inequality and the isochronometric theorem are linked. But maybe let me put, maybe if there's time, I might talk about the linkage, but I'm not convinced there's going to be time.
Yes.
So I did talk a little bit last class about these interacting gas models, like models of rotating stars. So here's another interacting gas model. So imagine that you represent the density of gas in a container now. you can think about various kinds of energies. So the energy associated to mu. Well, to be honest, I'm mostly going to be interested in the case where mu is absolutely continuous with respect to Lemay. So mu of x given by rho of x times the Lemay measure. So the energy associated to mu, there could have different contributions. So in the interacting gas model I described 2 days ago, there was an internal energy associated with the resistance of the gas to compression. So that would be something like integral of u of this density rho, and then integrated against the Lemay measure. And in that model, there was also an interaction between a little bit of gas here and a little bit of gas there by Newtonian potential. And so that kind of energy would typically take a form like this. So this is like an internal X, so I'm going to call this mu, W mu. And you can imagine a third term as well if you want, which would be like a single. This guy's quadratic, it's a pair interaction. You can imagine an interaction through background potential as well. So this is kind of self interaction. Quadratic term. This is an interaction with background. And this first term would be a kind of internal energy. Internal energy. Resistance, equation of state, resistance of compression. And what's to notice, about the structure of these three terms is that the first and the last term are local, the middle term is non-local. Right, the middle term is non-local because it involves interaction between x and y at a distance. The last term is linear.
Here, what's our definition for local?
Well, so it depends only on the density at one point. So you get the total in this total energy, you get the total energy by summing up the contributions from different single points. In this guy, you don't get the total energy summing up the contributions from different single points. You get total energy by summing up the contributions from different pairs of points. The last term is linear. The first term is non-linear. And the second term is quadratic. So the second term is linear on the product space down across itself, but it's non-linear. And so I'm interested in if I wanted to show things like unique, if I wanted to kind of minimize this energy among probability measures on M, if this was a physical model, the minimum state would be a stationary state for the gas. And it's often interesting to know things like, is the stationary state, is the minimizing state unique or not? And if the energy is convex, then typically that's a nice technique for showing the minimum. And when it's convex, it simplifies computation because you can't get stuck in a critical point which is non-minimizing. So convexity show uniqueness and stability of minimizers. And also helps and to characterize them. So compute numerically and characterize theoretically. And of course, you can, it's very classical to ask for, then the question is, what do you mean by convexity? And it's very classical to ask whether E is convex along line segments joining mu naught, mu1, where you shrink mu naught, you grow mu1. And sometimes it is, and when it is, that provides you with a lot of insight into computing characterized solutions. There are functions which are non-convex for the usual interpolation, and then another question you can ask is, are they convex along the D2 geodesics during pairs of probability measures? So there the picture is, instead of evaporating mu naught and growing mu1, I'm going to move mu1 to mu1, and that's where the transformation comes from. And so you can either that's the mu naught, so 1 minus cos mu naught, this is mu1, or along so I'd like to understand when is, for which kind of choices of U, W, and D can I expect this energy to have nice convexity properties along D2 geodesics? And so it's pretty easy to answer this question for W and V, and it's a little more subtle for you. But okay, so let's say I'll do the case W, and I'll leave the case V as an exercise, and then I'll talk about the case. And maybe I should also, maybe it's, a sum of, if two functions are convex and you add them together, you get a convex function. So the same thing is true here. So if these guys are convex, you usually the sum is convex. So
are we looking for global minimizers?
yeah.
Okay.
We're also looking at we're also looking to rule out global minimizers.
Okay.
I mean, obviously, local convexity tells us something about stability of local minimizers as well, but much harder to show. So the dilemma is something like W and the script W with UT geodesically convex. And to some extent, you can, if W was uniformly convex, you could probably get uniform convexity here, and if it was semi-convex, you could probably get semi-convexity here, but with some caveats. And W is strictly convex. Then script W is strictly two geodesically convex. I hope, unless mu naught is a translation of mu1. Well, okay, so these energies that I just erased are translation invariant. So if I took M to be the entire space Rn, and I took mu and I translated mu, and I computed the energies of two guys, they would have the same energies for each of the three terms. And so it's clear that the D2 geodesic interrelating between mu and one of its translates is actually the translation of the measure from its initial to its final position. The W is going to be constant along that. And so I can't have strict condensity if one guy is to translate the other. And this is actually a clue that you can't have, when W is convex, you can't hope to have ordinary linear interpolation condensity script W, because I could have two minimizers. One, a minimizer and a translate. If I shrink one and grow the other one, it's probably not going to be a minimizer anymore. So how does the proof go? So we need to remember what the geodesics look like. So that's mu naught mu1 probability measures of M. Recall geodesics take the form US is image I S of XY is the Euclidean geodesic joining X to Y. And so now I want to compute script W along such a curve in US. So it's like the double integral of W, let's say WAB, USA, USB. Well, we had an even better there. So I don't want to have to write this as a quadruple interval if I can help it. Well, maybe I can avoid doing this. So yeah, I can do this. M, and I'm not sure I can avoid it.
A minus B, wasn't it?
Yeah, it's A minus B, right. So I guess I would have something like W of this density, pi s of y minus pi. Yeah, just W pi s minus. Okay, let me make my life simpler. Let me just deal with absolutely continuous measures. And then I had a nicer characterization, which was that this was also 1 minus s identity plus s gradient u push forward the initial guy where u was a convex function. And so,
Okay, so people in the chat say that subscripts are difficult to read. So maybe making them bigger or something.
okay, thanks. So basically the A here is going to be like 1 minus Sx plus S u of x. And the B is going to be 1 minus Sy plus S u of y. I probably have gone off the screen for people on the chat. And then I'm integrating the x to u naught, x to u1, u naught y. So the argument of w here is 1 minus s x minus y plus s grad u of x minus grad u of y. And then I want to be able to apply the ordinary convexity of w to say, yes, this is over here. This is less than or equal to the double integral naught of x u naught of y. Um, 1 minus s w of x minus y plus s w of x minus u of y. Then I can break this up. And what I get is script w of u naught. And now grad u pushes forward mu naught to mu1. So this is like w of, I don't know, new variable again. I'll go back to a and b. u1 and a, u1. So this is script w. And so that's the convexity of script w along these d2 geodesics. And so that's on the first part of the theorem. And then if I want conditions for strict convexity, I need to go back and look at this inequality. And if w is strictly convex, then I'll get strictly unless x minus y is u of x minus u of y. Mu naught cross mu naught, almost every y. And so if I rearrange this a little bit, I would get x minus u of x equals y minus u of y. mu naught, almost every x, y. And so that would be that this is constant. So this is independent of y, that's independent of x. And what, so let's call it constant k. So i.e. strictly convex unless u of x is x minus k. Translation. And so the condition for strict convexity exactly recaptured that when I translate u naught to mu1, the energy doesn't change. U naught was mu1 unit to on grad u and state correcting the translation. So that's basically what. Other questions? So then we want to come back to the internal energy term, which was the nonlinear one. Well, okay, so if So there's one that V is convex and script V is convex. If it's strictly convex, then script V is strictly convex, and then there's no, for V, there's no qualification for translations. And so I'm going to assume, so what's the theorem? The theorem is that if U vanishes at the origin, and you have a map on positive reals, which takes values but this map here is A convex and E non-increasing. And you can do convex. On, let's say, these probability measures. And then always assuming they come back to bias. So there's this kind of funny condition. So maybe I can give some examples first. So e.g., so maybe I don't know what to call this condition. Call it star. So if so the typical thing that you do with U is you take U to be like a power. So and I think if and only if M is bigger than 1 minus 1 of convention. Because when I want to write lambda n of U of 1 over lambda n for this guy here, that would give me lambda n times 1 times 1 over lambda n. So I have lambda to the n times 1 minus m or minus 1. And so basically, in this case turns out to be linear. The equality case is linear. So if n if this exponent here is bigger than or equal to 1, and m is bigger than or equal to 1, I'm in good shape. Then this is, oh, careful. Right, the equality case is non-linearly negative. So I need both A and B. So let me just draw the pictures for a second. So if I just think about lambda to the power, when P is bigger than 1, it looks like this. So that's convex increasing. So convex is good, increasing is bad. When P is between 0 and 1, if I put a negative in front of it, so between 0 and 1 minus lambda P, then it's convex decreasing, that's good. And when P is less than 0, and I do lambda to the P, then it's convex decreasing, that's also good. So this satisfies A and B, this satisfies A and B, this satisfies A but not B. And if you change the sign of it, it satisfies B but not A. So this is somehow the bad range that you want to stay away from. So you want this to be less than 1. I.e. 1 minus m bigger than 1 over n. So this is clearly the threshold case, but
Sorry, I was in the chat, so I missed a couple of things. What's this equality with the lambda?
sorry, which one? This one here?
Yeah.
Oh, on the left hand side, you should have it here.
Okay.
Is that better?
And the u. Yeah, okay.
Right. So the m minus 1 here is just, it's some fudge factor that gives you the right sign that accounts for this change of sign. So I'm not worried about that. What's perplexing me is that it seems like I want this exponent to be less than 1, but here I'm asking for it to be bigger than 1, and that's confusing to me. Maybe I think we should think about m very large. So if m is very large, this is very negative, and that's good. That puts me in this condition here. M is very large. Very good. M is very large. Sorry, here we go. So these are equivalent conditions there. Okay, great. And so let me see, since time is short, I think I'm going to not try to prove the theorem. I think I'm going to rather derive the Bruner-Test. I'm going to try to derive the Bruner-Test inequality from the limiting case where n is equal to 1 minus 1 over dimension. So I'm going to not prove the theorem. I guess I'll save that for after spring break. But I will derive the Bruner-Test inequality. So I'm going to choose, in this example, I'm going to take m to be 1 minus 1 dimension, and I claim it applies to Bruner-Test. The each that's introduced even up a certain frequency on these absolute proper measures. So take you so in particular negative n times s. N doesn't matter, the negative sign does. Take K0 and K1 to be subsets of Rn. DUI is basically a characteristic function of Ki divided by volume of Ki. And then define US. Then you choose geodesic with these endpoints. And then what do we know? We know a couple of things. We know that because US takes the form 1 minus x times identity plus x grad u for some convex function u. We know that the support of US, for simplicity, take these to be compact. And I'll have a positive measure. If we don't have positive measure, you need to handle it so that you need to be able to define properly measures. Positive volume. So the support of US is going to be contained in 1 minus s times the first set plus s times the second set. And some grad u pushes forward K0 to K1, grad u goes to K1. And then the other thing I know from the theorem tells me that the internal energy of US is less than the convex combination of the internal energy of U0 and the internal energy of U1. And so for this choice of U, minus n integral over K0 of 1 over volume K0 to be 1 power 1 minus 1 dimension. And then it's a living integral. So it's going to be an integral over something volume K0. And so this inequality here, I have all these minus signs floating around, tells me that minus u of US is bigger than 1 minus s volume K0 to 1 over n power plus volume 1 over n power K1. So this is exactly like the right-hand side of the test inequality. And I need to see that this thing is less than minus u is less than the left-hand side. And so let's look at u of US and then we're done. Let me call the density of US rho s. And now basically what I want to do is I want to use, I'd like to use Jensen's inequality. And so to use Jensen's inequality, I need to divide by the volume of 1 minus s K0 plus s K1. What else do we multiply, right? And this power here is power less than 1, between 0 and 1. And so it's like a concave function of rho. And when you have a concave function and its value at the average is bigger than the average, then its value, sorry. So this is the inequality. So I can take that, I can take this outside the integral. And then rho s is a probability measure, so the integral is 1. And then but I still have this volume in the denominator, which cancels this except for this power -1, so that's exactly equal to n volume through the K0 plus SK1. So you see that somehow the Brindin-Kowski inequality is hiding in this d2 geodesic convexity of these inequalities, at least for this choice of. And so there's a little bit like an LM norm, except here m is less than 1. But in the lemma, or in the theorem, m could have been bigger than 1 as well. And if you think about the limit as n goes to 1, since 1 is approached to both sides like you to satisfy it, it turns out you can also take u of s equals s log s, satisfy star. So you can also take Boltzmann a tree, and in fact, this guy is the limit m goes to 1 of that guy in some sense. Okay, so I guess it's a reasonable place to end. I guess our first agenda after the break, 10 days from now, will be to prove the theorem. And the other things that we have on our agenda are, well, okay, so I guess we can talk about the other things we have on our agenda now. Are there any questions? Are there any questions from the remote participants?
No, they were saying that they could understand, but maybe it was a little fuzzy. So like 2 cameras, or like maybe putting this one close, or some solution like that.
I think that I'm going to see what the feedback is.
Yeah.
But I think the likely solution is we're going to go back to virtual.